So, dear participants, just we will start our second session. I was introducing Dr. A. Rajni ma'am, who is a professor and head of department of JNTUH, University College of Engineering, Hyderabad. She has done her BE and ME from NIT Trichy and completed PhD from IIT Delhi. She has industrial experience from 2002 to 2003. She was an engineer in HelloSoft Solution. Then she became assistant professor in BREC WC JNTU University from July 2002 to 2003. And then she joined JNTUH, Jawaharlal Technological University, as an assistant professor of level 10 in 2003. After 5 years, she became assistant professor level 11 in JNTUH only from 2008 to 2014. Then again, assistant professor at level 12 in JNTU from 2014 to 2017. Then she became associate professor from 2007 to 2020, and now she is acting as a professor. She is working as a professor and acting as a head of department in JNTU H College of Engineering. Her research project include design of energy monitoring and management system using IoT, and development of coal mine safety monitoring and alerting system using IoT to mitigate coal mine accidents. And third, development of avalanche forecasting system using Internet of Things to mitigate avalanche hazards. Her international journals include EEG-based interpretation of human brain activity during yoga and meditation using machine learning in Elsevier Journal. Neuropathic and yogic intervention in the management of coronary artery disease, which is a systematic review in European Journal of Molecular and Clinical Medicine. Her national journals include localization of snow avalanches from infrasound signature using acoustic vector sensors and digitization of electrocardiograph datasheet through image processing techniques in IUP Journal of Triple E. I will request Dr. A. Rajni ma'am to please start your presentation, ma'am.
Yeah, thank you so much, Anup, for your nice introduction to me. Uh, I need to share my PPT.
Yes, ma'am.
Yes. I hope it is visible.
Yes, ma'am.
Yeah,
Can you please put it in full screen, ma'am?
yeah. Okay then.
Presentation is coming full screen.
Yeah, it is coming now.
It's coming, ma'am. Please put it in full screen. If
It is in full screen only.
here it is showing like Windows.
I think it takes little time.
Okay, ma'am. You can start, ma'am. It is clear
To
only.
avoid and sharing. Still, it is the same thing. Yeah, no
Like
problem.
Windows is coming, like file, something is there. No, from beginning,
Mm. Once again, I'll do it. Continue. So it need to be opened in Chrome, this tab, or
just as you have uploaded now, na, you
yeah.
can share like that
I mean,
also.
if it is instead of window, what it
Mm.
is telling me that you need to open with the tab as a tab. So even then,
Google, directly we can go to Google and open it.
In corner from beginning, it is there,
Madam,
ma'am, one option from beginning.
Yeah, in corner.
Below file, you can see from beginning.
Below file. On my tab,
That Windows is, ma'am, left corner on the top.
yeah,
File
yeah,
is there, another file is there.
yeah.
Below
That
that, from
I,
beginning.
yeah. That I know. But still, it is not coming. Before
Okay,
also,
start. You can start, ma'am. It's
madam, otherwise we zoom it, madam. It will work out. Zoom it, madam.
in my, it's showing that in my system it is opened in a full mode, but it is not showing in here.
okay, ma'am. Maybe it will take some time, ma'am.
Okay,
Just,
then I think.
ma'am, you can start, please.
Okay.
Mm.
Good evening, all. It's
Good evening.
wonderful to be part of this ATAL FDP. Thank you for giving me this opportunity. Uh, I think I'll start with the title. What I want to present today, that is beamforming in MIMO communications. So I think to what is the flow of my presentation is what is past and present, what is that we are looking for future in, especially in 5G and beyond 5G, especially towards 6G wireless communications. And then I'll present the essential technique, which is one of the technique which uses beamforming for beamforming is a technique for multi-user MIMO communication, which helps us to go towards 6G communications. And I will show one example with beamforming problem with artificial neural network architecture. And then I'll conclude with what are the different other techniques which will be helping us in building these 6G communications. So this is the flow of my talk. And then for I think previous last 4 days you've been listening to several aspects of mm, several aims and abilities of the concerned 5G and 6G communications. In a nutshell, I just want to look into these aspects once again for the importance. Because of its importance, I'll just refresh a few of the things and I'll go to the next slides. I think we all know from in the beginning, it started in 1980s. Our analog based on the cellular concept, the first 1G or otherwise analog modulation schemes and frequency division, multiple accessing methods. It has started around 72 80s in the first generation of communications. And then it has emphasized and enhanced into by using the time division multiple accessing techniques into 2G, where we could be able to transmit apart from the voice very small data we could able to send. And then the modulation scheme which uses is Gaussian minimum shift keying technique is been used for this second G, 2G wireless communication. And then I think 3G, it's around 2000s, both voice and data. And then it is aimed for data rates. I think in the previous generations, it is only up to kbps, kilobits per second. And it has emphasized into every time in tens we will be doing, so it goes into 10 megabits per second, so emphasized. And then from 2000 to 2010 it's around 4G, fourth generation, where it aimed for 100 megabits per second data rates, and then the new modulation scheme is orthogonal frequency division multiple accessing schemes, and it was much more popular where we could able to use these data rates both in terms of apart from data, voice data, and then also videos. And then, as that's not sufficient for the live chats, we have started, I think, Skype and all are being used in those generations. Further, to have a live chats and all, beyond 4G, it is 2020 onwards. We are in the era of 5G, where it has around 10 gigabits per second of the data rates, where we are able to use seamlessly downloading several huge files and huge movies or videos in all the online platforms. And then it is possible because of these data rates which are available because of the technology upgradations. And then I think we are going beyond 5G for the emphasis, because we want to connect to several Internet of Things and several, and then we want another highest requirement is the augmented reality and virtual reality, where you are otherwise immersive technologies. They are also called. I think you will be feel like you are somewhere even you didn't go. So that's sort of a continuous, seamless, and real-time applications, especially for those things you require really large data rates for so many users. That's the crux of the problem. For those cases, I think you really require a huge database apart from several other angles which you need to think when you are integrating a mass communications. It is like huge user you are going through. So I think that's the essence of 5G and beyond 5G. The essential techniques are technical aspects which has been used, or rather which made the that making it possible is only because of the higher new techniques which we are trying to understand and then implement with respect to hardware. That's what MIMO, multi-user, multi-input, multi-output, and then multiple users, MU, multi-user, multiple input, multiple output is the technique right now we are thinking of, and in terms of so many places, even within India. And I think in this scenario, 5G onwards, our country has become a forerunner, surely, because both IIT Madras, IIT Hyderabad, IIT Delhi, and IIT Bombay, there are several places where they've been, government of India has been given opportunities for all the people around in the institutes, as well as many startups have come up, so that we will be implementing, and for that implementation, all the portions of the blocks and layers and verification are being done with test benches, and several applications are being tested at different states.
Madam, sorry for the interruption, madam. Madam, please put it in a slideshow, madam. Slide is not visible.
It is in slideshow only, madam.
Otherwise, you can
I can increase the size. Yeah. Is it visible now? Is it visible?
Madam.
It's not visible. Is it going on? I mean,
going on. Slide is going on, madam. Slide is moving. No problem.
Ma'am,
okay.
press F5, ma'am.
I am with F5 only, but still it's not going.
Otherwise, you open with Google slide, madam. Google slide.
I think then I need to send to my mail and then because so you want me to do that way?
Yeah, please, madam.
I think maybe I'll try to open with my mail ID. Okay, just give me 2 minutes time.
Yeah, no issue, madam. No problem. You can take.
Now it is okay?
Madam, okay.
Okay. So, okay, what I'm
Yes,
speaking is beyond 5G. I think the number of opportunities in and around Hyderabad as well as in our country, where we are forerunner in this case. We want to, in the previous years, especially coming to 2G and 3G and 4G also, I think we've been not a part of all the all the implementation, or otherwise in the, especially in the development area, in terms of application layer, or otherwise in terms of a hardware and software requirements. We are not part of that one, but good. It's good that we've been part of it. 5G, we've been part in from the beginning. So all the European countries and other continents are looking for the support of Indian people and Indian researchers and an Indian um, industries. They are looking for that one. That's where in this area there is so much of research is going on in our country. I think just for the information for the participants. I think the techniques which are making this feasible are the multi-user MIMO communications, which has been one of the part technique is beam forming. I think we will see that in an elaborate way in the coming times. So I think the 5G especially gives us a seamless connectivity without any interruption, and we expect very high data rates. And then wherever you are, maybe now we are in Hyderabad, we don't feel that connectivity problem. If people are going for tech, going on mountains or any other villages, even in that case, we want a complete. I think Government of India, most of the aspects, I think you might have seen Smart India Hackathon, the very intention to make it a complete coverage of all the nook and corner of our country. There are several problems which are being posted in, especially from different sectors. This coverage, even CDOT, and is continuously on this goal of complete coverage. And then for this to happen, and then the other thing is like making it augmented reality or virtual reality, where we expect you can feel and touch also. That's the tactile internet. So in the coming days, it's been expected. And near real time is like it's less than a millisecond. And complete coverage means it's almost like 99.999%. We cannot make it exactly 100. So it's like a gold rate. You will be writing it as never it is 100%. It's like, because that's the standards. We are trying to make it complete, high data rates and seamless connectivity. So this is what is being expected out of the 5G and beyond communications. I think for this one to happen, some of the other aspects to happen is like a machine to machine, which is a type of communications, which is also part of IoT. And we also want everything we want. We want to work all these things in with very low batteries, and then despite that, it should have very low cost, and then it should be simple. All these are our desires to achieve, which drives the technology. And then that's what a super real time and reliable. That is the reliability. That's, you can trust that communication and information. And then very low latency and very high user density. And then instantaneous connectivity. That means you should not have any delay. The moment you touch it, you should be able to see the everything. So, and then it also expected to use the cloud services. And then especially in the coming days, because low latency in terms of medical, it is very highly, because robotic surgery are remotely, the doctor will be sitting at some California, and then the patient might be there in somewhere in the remote place, but still he can conduct the surgery. Then in that case, you can expect that what is the latency I'm talking about, because it should not have any. I think in nanoseconds you should be. That's what is being required. If you want to really use this technology for the health sector.
Hello.
Ma'am,
Ma'am. Dear participants, sorry for the inconvenience. Some internet problem, it seems. Ma'am will rejoin within 5 minutes. Thank you. Thank you for your cooperation.
Sorry, yeah, very sorry. There is a network issue with respect to power on and off. I think we are talking seamless connectivity, and then
No problem, I mean, this it happens sometimes.
No problem, madam. No problem.
so surely the power is the more essential thing to have
Essential.
the seamless connectivity. Yeah, just I hope it is visible.
Yes, ma'am.
Yes. Okay. I think in terms of health, if it is to be really a real time, then I think latency need to be really in nanoseconds. That's the scope of the work, which is ahead of from 5G to further Gs. Because obviously, really to make it into practical, really we really require a real time. Okay. As far as coming right now, 5G, whatever it promises 10 times throughput compared to the previous generations, and 3 times more spectrum efficiency compared to the previous generations, and also it also promises 100 times the capacity which is existing. And then it's if you put it all those things in values, user data rate in terms of 100 megabits per second, and mobility it is expecting up to, even the user is moving at 500 kilometers per hour, because there are certain trains uh, which which are going at that rate, but still we want to have a connectivity. So even then, in that case, it is promising to have up to that mobility, or otherwise the velocity. Even if that rate the user is changing, user is moving, still we want to have a connectivity. And then we want to have a downlink peak data rates around 20 gigabits per second, and then uplink peak, because downlink is something that you try to download, you don't want to wait for that one, so that's expected to be more than the uplink peak rate. And then downlink peak spectral efficiency around 30 bits per seconds per hertz. You can see that this to be achieved, there is a lot we need to understand with respect to modulation techniques, as well as the error correcting and controlling techniques. And then these are all results are being given for downlink 8 antennas and uplink 4 antenna system. These are the critical values. And then it is expected to give us 10 power connect 10 power 6 devices per kilometer. That means a high density. And then the energy, which we have talked, that it should be 100 times of previous. That means it should be using 100 times less than the previous devices. And then the new radio expects to include diverse deployments. That means you different vendors and different conditions, and then diverse spectrum utilization and diverse services. Especially you will be connecting to your fridge, you want to connect this internet of things, where all the devices will be connected to the internet. There will be a machine in the industries also we want to connect, and all the home automation we want to all connect to the internet. So for all these diverse devices, diverse deployments, you should be handling this one. For all these things, we need to understand how we use, how we design the waveforms, how we use the spectrum efficiently, and then how we handle the traffic, and then how we design the network to do all these different accessing different deployments. So I think these are the research areas. By seeing the promises and requirements from 5G and beyond, The one which is especially there is a lots of work which is going on in the standards, especially at the physical layer, and then access layer and the network layer. And then physical layer, we can think of waveform design. I think wideband OFDM and filtered OFDM and universal filtered multi-bank filter bank multi-carrier and filter bank multi-carrier and generalized frequency division multiplexing and adaptive OFDM. These are all the techniques which are being at physical layer for the waveform design, which can be understood for the development of the physical layer system. And then it's like enhanced mobile broadband. These are the terminologies for the 5G and beyond. And then massive machine type communication, so that you will be connecting the machines onto the internet and the machines will be working according to your wish. You are sitting at a remote location, but still you can make it machine to work in a automation in a bigger industries we are talking about. Also small machines in terms of a home automation. So, and ultra reliable and low latency communication. I think these are the terminal, for the terminology sake I have written here. URLLC and MMTC, all these things are the terminals which you need to understand when we are reading any research paper or journal in these areas. And then as I mentioned, the modulation and the coding techniques and understanding the channel propagation characteristics and then how we model them, that's what builds the um, research area, because you need to mathematically model the things and then simulate the things, because before you really venture into onto a hardware, you need to do quite good number of simulations to understand these aspects. And then I think this new millimeter wave communications, whatever we are talking, it is in terms of a gigahertz. So it boils down to the wavelength of millimeters, around 30 gigahertz. So obviously beyond that one, we can beyond 30 gigahertz, we also call a extremely high frequency or terrestrial communications. And we need to handle heterogeneous networks, maybe small cells, device to device, and different architectures. And then for all these things, how we develop the radio access network architecture RAN, which is also so much of work is going on in our Hyderabad also. So for all these things, we make sure that we also, in terms of a network aspect, we need to ensure quality of service and how much energy you can save with your research ideas. By using that research ideas, how much energy is incorporated and saved for this one, how much spectrum you are saving by this good modulation technique, and how best you can use the radio resources so that you can provide more number of users the services. So these are all the open challenges which have been there in the past and then present, whatever state we are, and it is going to be far beyond now. Um, for the frequencies, I think if we are going less than 6 gigahertz, we call it as sub gigahertz communications, and then 24.25 gigahertz to 52.6 gigahertz. This is the area for 5G. Another band is being allocated, which we call it as the millimeter wave communications. And then we know that from 30 gigahertz, it is more than extra high frequencies. So for all these frequencies, taking into consideration, the distances are very small. It is like short propagation distances. That means whatever you are incorporating as a cell is of a small cell sizes, because it is in terms of millimeters to meters and so. So that's where the millimeter wave communication, because 5G and beyond millimeter wave communications. So designing the antenna suitable for this application, because you need to design the antennas, millimeter wave, which antennas which produce that frequencies, and also receive those frequencies and handle, and your hardware is also should handle this high frequencies. So you should be designing. There is a lot of scope in terms of antennas, because how you design that, how you best design this antenna structure in a given size. That is also a open area, because obviously we have seen that from past to present, the size of the mobile phone is been shrinking, and then now I think little bit more size, but the thing is the size is been shrinking. The size is shrinking because of what frequency you're operating. And then if you want to still provide the things, you really work on the how you design the ideas, and how you handle the impedance matching, and all those things you need to. There is an open, this is continuously open problem in terms of antenna design. For a particular application, it will be different, because the device, IoT device you want to take might be different size or different place. You need to keep these sensors, especially for the autonomous vehicles. So that's an open area. And then I think to understand this millimeter wave communications, how they travels, whether it is by a line of sight, surely it is line of sight, blocked and reduced by trees and walls and buildings. So it is also absorbed by gases and moisture. So once it is absorbed and reduced, then you won't be getting the correct signal at the receiver. So all these things in terms of which receiver design need to be taken into consideration about the wireless channel. All these things, frequency flat fading if it is coming, or frequency selective, or and also spatially rich, because you are using multiple inputs and multiple outputs you are using. So you have a more possibility of more scatterers, or otherwise more scatterers. That means the coherence distance is very small. That means the signals which are been coming from different antennas, the coherence distance is smaller. It also depends on what frequencies you are operating and the design of antennas. Okay, so I think there are the open problems we are been seeing. First of all, we'll understand somewhat in this 5G area, some of the things in terms of a signal processing, and especially in terms of a beamforming. So with respect to MIMO. So MIMO, all of you are aware of it, that is multiple inputs and multiple outputs. It is both spatial multiplexing and spatial diversity. That means you are sending the same information over different signal paths, and then say receivers will be receiving. It means that receiver is receiving multiple copies of the same signal. Then within the same slot, it is receiving these multiple paths, or within the, you are using different time slots to send your information, or different same frequencies you are using the to send your information. That matters what is the processing we need to do with the receiver. Especially in the mobile communication, we will be taking the rally channel conditions sometimes. But the thing is, when it comes to the multiple paths, this channel can be modeled as simply AWGN. That's where the receiver design will be simplified, because if you want to use a channel which is the rally channel conditions, the design of the receiver with an equalizer, the complexity will be receiving. But if you include include at the transmitter side multiple copies, then you can model at the receiver side with a simple AWGN receiver means it's like a correlator, or otherwise a matched filter will be working fine. So that's where the simplicity with the complexity, we are shifting to the transmitter side rather than the receiver side, um, with the enhanced benefits in other areas. Okay, to understand the MIMO signal processing, I think it is also called as a space-time block coding. It's also, we need to understand MIMO coding or pre-coding, how we send the information from the multiple antennas to the multiple receivers, so that we will be receiving and it will be demodulated. So one of the another good thing is that channel state information is not needed in MIMO. That's another thing. So the first scheme which uses the MIMO technique, which has started in a long back in 2000, two antennas and two by two MIMO, which is also called as a Alamo T space-time coding blocks. We will call Alamo T codes. This is the starting one. I think you can search there is a lot more in terms of research papers. Overall review has been, I think you can look into that one, especially in the 1919 paper. I think it has been given a directive transatlantic communication practices, which are being developed in the First World War. And then there is a paper in 1988 beamforming, a versatile approach to spatial filtering. And by 2000s, I think in terms of research, it develops first, and implementation, because of the hardware availability and all, happened in the area around 2000s. That's where all these challenges can be implemented from a research perspective. You can refer this aspect of beamforming in this review paper, a versatile approach to spatial filtering. Okay, I think first we will see some of the aspects of what is this, the terminology with respect to beamforming, and then because further we'll try to understand how we can do with a certain one example or one problem at a hand. And then all this wireless communication, especially we talk about multiple input, multiple output communication. We are aiming that you have the information of user information, and then you try to send the information in that particular direction itself, so that it doesn't cause any interference to other users, and it will be reached for a long distance, because your beam you are directing in a desired direction. So beamforming, I think most of you might be knowing analog phased array. I think phased array, I think to start with the antennas, each one of us know that using more than one element of antenna, you can combine them if you properly feed with the current and proper phases. You can make sure that all these omnidirectional antennas can have a beam direction. So that's what is the array concepts which we study in the antennas. So the same concept we are trying to understand and implement at those frequencies. That's the crux. Is the problem is the concepts will lie long ahead, but the thing is, it is the problem. It is the problem which we are understanding is in terms of implementation. The where this problem might be more challenging is the frequencies by which we are operating, because you are operating at a gigahertz and delays getting in. First of all, frequency oscillators designed at those gigahertz having a stable frequency itself is an open problem. Why the research has been, I mean, why it is taking more time to go for large data rates is only because you want to work at a gigahertz, and then you should be having a source which generates those things. So, and then it should be stable. So even the slightest thing, it makes much more disastrous in the when you implemented the receiver side. So the problem is like designing, working at those areas, at those frequencies. Okay. So I think beamforming, these concepts are known ahead of the times, but we are talking about the implementation and working cases verification that's been done in these times. I think we all know that with an antenna arrays, we can make sure that you can have a narrow beam directed in a particular direction. Okay. I think that we can be, I think all of us know that an antenna with an omnidirectional pattern of beam radiation pattern, you can make it a directional radiation pattern by combining proper phases of the inputs and then feeding it into each element and then seeing the output pattern. So in the beginning days, if it is called as a switched beam in the previous switched beam or phased array antenna. So later, that means phased array. So you know what combinations will combine and what direction. So it's like a fixed directions patterns. It's like, so we call it as a phased array antenna. But I think later times in the process, we can have also adaptive antenna arrays where you combine the signal processing into making sure that you have any desired direction of beam pattern. So this example is showing that there are 8 elements which are equally spaced with the d distance, and then it combines to work as an array. You can have this sort of a combination of antenna elements in any shape. But what is that desired direction based on the shape decides? It is like a two-way problem. If you want a desired direction, you decide the pattern and combination of those elements, and then you get the desired pattern. Or otherwise, you decide the pattern and then combination and distance, you will get the desired direction. Okay, it's two-way problem. One is, we'll say that one. So you can have different shapes of antenna elements. It was shown here, a circular antenna array. You can have a rectangular array, square array, or otherwise lattice type structure, or otherwise a random array. This is all possible. I think there are I think there are good number of I think resources as well as tools, simulation tools to understand this millimeter wave simulations, antenna, especially antenna simulations, all the antenna pattern, beam direction, and S parameters inclusion, and the impedance matching. Like Cadence has taken over COMSOL physics. So now it is called as a cadence only. So within that one, you have V2S or simulation tool. There are tools, simulation tools for this, especially working in this area. Cadence has now. And there is a microwave office, which are the tools available for at these millimeter frequencies. So I think we started with overall 5G and then MIMO, and then to understand a subtopic of this one is which is giving us the beamforming. I think we have seen that why beamforming is adaptive arrays, which should be my told adaptive arrays. Adaptive means what? What adaptive area means? I want this because the user direction is not fixed. User will not be staying at same place all the time. Based on, so I can fix my beam pattern like this and then do in an analog fashion, but I should be changing with time. That's where the adaptive arrays comes into picture. So how I should make sure that this beam is directed to my user direction, it will be depends on what my input is. So this so and so is my direction, then I should be, there are antenna elements in an array fashion, whatever the fashion, whether it is circular fashion or a linear fashion or otherwise rectangular fashion, there are available elements, and you need to decide, you have a direction given from, got from channel information between base station and the user, then you need to steer, you need to steer your beam in particular direction. How the direction depends on is the combination. So this is the, with the signal processing techniques, what we will be doing is we'll try to find out the combination of these weights, so that the resultant will be in that particular direction. That's the problem. It's an optimization problem. How best you design your weights of this combination of several antenna elements to get into that particular direction of the desired user, and having a maximum peak in that direction, and also have an a minimum signal strength in the interference direction, because you want to, that is also the other aspects. It's not only that you steer your beam to a particular user direction, you want to reduce the interference to the other users also. There are several interferences, we call it as a multiple access interference and co-channel interference, and then so many, because you are in the same area, then whatever is being received, if it is in the same channel, it becomes an interference to the other user also. All these things, it's an optimization problem in terms of a signal processing. That's where this is, when you want, there are some inputs, there are some expressions you can write the combination and you can solve it. That's what has been optimization problem. So you can use all the machine learning techniques and all the existing openly available techniques to solve this problem. Once you, any problem at hand, put it in terms of a math. That's what is going to happen in the, and I will explain how we do. And that's what adaptive beamforming is. Make sure that you will get into the desired direction based on the requirement. Okay. I think before further understand this aspect, I just want to explain with an example. All of us, even if we close our eyes, we can say from which direction someone is calling us or someone is talking. So all these things are possible because we don't have only 1 year rather than 2 years. God has so merciful, and then God is already knows the things, and then the ability of us to understand the direction has been incorporated in giving not one but two. So what is that we will be doing is the entire, it's like 2 years or two antennas, and whatever processing is been happening, it is in the brain. Okay. What is that it is doing is already all our existing architecture in our brain. It is trying to understand what is the slightest delay between both the signals which it receives through those 2 years. The distance between the, how much, it all depends on our head size and face size. So that's the big, I think there is a range for those things. That's the range. And then what are the frequencies we hear? Obviously, that is also limited up to, there is a audible band is up to less than 20 kilohertz based on the size of our face has been manufactured. So So that's the delay ensures that we can able to understand the direction. So that's what is the concept is being used for this antenna arrays, especially beamforming or further. You can beamforming is in if in one way there are other terminology I need to tell you. Um, Beamforming is something that you already know the direction and you are trying to find out the weights, okay, so that it gets into certain direction. There is another reverse problem, we call it as a direction of variable estimation, DOA. What it means is, like, you are receiving with a certain signals, certain antenna elements, and then by combining these signals you should be able to now know which from which direction it is coming. So this is one direction problem, this is another direction problem. Both are required at, if you want, if I'm talking at the beamforming, I need to know before that what is the direction I'm receiving that signal. So this is both problems are at hand. We need to solve in this MIMO if you want to really use this directional pattern, receiving in particular direction alone and reducing the interference. Okay, this is a fixed one which I'm showing, switched beam. It's like an open loop problem. You already have beams generated with your antennas, and then you will be choosing out of them one based on the direction of the user. It's like picking up. There is no adaptiveness here. That's where user one is there, user interferer one and interferer two is there, and then you choose based on this is the direction of the user and you will be choosing that direction. But it doesn't reduce the interference at that points because this is the fixed beam patterns. Okay, so you will be switching between these patterns. So I think it is also includes a predefined beams. So that means our switched beam is predefined beams, and only the user will be selecting from among them one based on the requirement. Okay, it also requires a RF network and M antenna elements and M directional beams it can give. That's the case, which will be a pattern is. Then another is adaptive array. So it is like a closed loop system where user is in a particular direction, interferer direction, we will be having a very small or otherwise very narrow beam in this direction with a small strength, so that it doesn't have any signal from this direction. So this is possible with respect to adaptive arrays. Okay. So adaptive array, if you explain in further in terms of a signal processing, you are receiving the signal from what is that different elements, antenna elements are this element 1, element 0 onwards, it is counted element 0, 1, 2, and up to m minus 1. There are m antenna elements which are receiving the signal strength, which we call it as S0, S1, Sm minus 1 of T signal strength from this one, and they are combined or multiplied with the proper weighting coefficients at that moment, and then they are summed, and then receiver will be trying to understand what direction it it is coming from. That is one thing. Or otherwise, you can see that we can also get the narrow beam in a particular direction and also a null at interference direction. This adaptive antenna or otherwise MIMO will also talks about space division, multiple access, and that means because you are directing in another only one direction, then other directions you can use the same frequency, but you can use the same time slot and then transmit same code and also transmit in other directions, because you are narrowed down to a particular direction. It also helps in space division multiple access. So I think we all know with the space division multiple access, because you are using this picture tells you that this is a the original past one. If you can have this smart antennas, we can also call this the smart antenna. Smart antenna because antenna is instead of doing an omnidirectional radiation, it is smartly doing only radiation in particular direction. There are users in this direction, and then this direction it is trying to give a peak in this direction, and the other direction. It is doing able to do at the same time. So space division also is possible because of this beam forming and UOA estimation. So it helps us the antenna gain in the other direction and reduces the interference, and which also helps this. It is also another terminology, smart antennas. It gives us the spatial diversity, and I think you can also call this as a spatial filter. All these things will work only if you have good signal processing, and then RF chains, and then a good a millimeter wave communication physical hardware. Okay. So these advantages, we can understand that we can have improved penetration, hole filling, and then we can reduce the co-channel interference, multipath management. It increases the system capacity. So I think with this fundamentals of this beamforming and the OA estimation, we will see how we can solve this with the neural network, because the today's world of tools available for us is artificial neural networks, and beyond that is the deep neural network. Deep learning is also, there are plenty of architectures available where there is possibility use. Why we want to use is also that because this is a I think there is a why we, when we can use the deep learning or neural networks or machine, you have, let us suppose the problem of image classification. Image classification means there are particular known images are there, and out of that it is picking only. So similarly, there are known directions. Directions are fixed, because but the only thing is when which direction which user comes in which time is the one which we don't know. But other things other than that, all the it is a known path, known plane, because you can get user direction out of all with this azimuth 0 to 360 degrees with an elevation depending upon where he is standing, or where maybe where he is standing, either in a building or in a car or in any other place. That's the only thing. So, but which user, which time, which location, which direction is only the thing. So you can map the entire thing to a using a neural network problem, and then this helps us. What is the advantage? If just like that, we don't go for all these all these existing architectures. But the thing is, how it helps is in real time. Because if you have designed with this network, with these architectures, and you have implemented and made it as an embedded hardware, then that will be working in a seamlessly with very less latency. That's the idea, because we want everything in real time. How best we can do is that this network architectures, if we can make it onto an embedded hardware, that's where it's. So that's the essence of going for this architectures. So we'll see how we implement with a simple, I mean, we are taking here as one example problem, how we have done with a neural network architectures. I hope I'm still, I mean, everything is visible. I hope I'm audible.
Yes, madam. Audible, visible.
Okay. Okay. I think when I have mentioned these two problems of beam forming, you should be knowing which direction you need to make that beam. So for that one, which direction means you need to, let us suppose you are receiving the signal from different antenna elements, and then use that signal, use the combination of those signals and find it out which direction. It's like our ears doing that, which direction. The same thing we are talking in terms of a signal processing, how we estimate the direction of arrival. There are there is a there are it can be, I think it can be several inputs also which are coming, like L targets means here L signals which are coming from going from a transmitting an array, and then we are receiving with another n elements. That's where MIMO concepts. We are transmitting with the m elements, and we are receiving with n elements. In all these cases, in this we need to understand or find it out the direction of arrival estimation from this antenna elements using the array. So I think the one of the example which is being shown as a Wi-Fi router, which is an omnidirectional antenna, means you are having a circular radiation pattern. If you want to have a beam formed in particular direction of the devices, like Apple or Apple Watch or mobile phone and laptop, based on that it can beam the send the information or internet information in a particular direction. It shows that information only. Okay. In a signal processing point of view, if you understand, there are, first of all, we'll talk with the direction of arrival estimation. There are techniques which are called as a music algorithm, which is also multiple signal classification. I told you that it is an optimization problem. There are signals coming, and how you find it out into the direction. I'll explain the expressions also. But overall, there are say algorithms which are music, root music, and then aspirator. These are, I think, 1970s, 60s signal processing. But they are worthy to read once again, because this gives us you much more information about the problem. So MVDR, which is called so-called minimum variance distortionless response beamformer, and also linear constraint minimum variance LCMD beamformer. This is also, I think I have given the reference paper now, that consists of all these overview and review of those methods. So what I mentioned also, I'm reiterating that because all this why we go for an ANN or a deep learning also is like we want it in real time, and how whether we can have reduce the computational complexity. That is also another angle we will verify before going for any other improvement or any other methods. That's what. So this was a model. This is a problem at hand. If you see that ANN architecture, I think what is that problem is, what is the array structure we are using is like a 4x4 antenna array in it's a square array. This means there are 4x4 means 16 antennas are there. Okay. Then the architecture is, there is an input layer, there is next comes the hidden layer, and then output layer. How we have used this problem is, I think I don't repeat for the intro of ANN because all of you know the artificial neural networks at hand. I don't think I need to repeat that information. I hope, or do you require any information on neural networks? Sorry. Anything you require from a neural networks point of view? Audience are aware of these things now?
Dear participant, please respond.
If they know about
Madam, can go ahead.
okay, basically.
Madam, madam, myself, K. Shekhar Babu from DNR College of Engineering and Technology, Bhimavaram, madam. But actually, what you are teaching is, we don't know that, madam, but is new to that my side, madam. That's why we are listening, madam. You explain, madam, in depth so that we can learn something, madam.
Okay, okay. Then it's okay. Then I think it's based on. Okay.
Yeah, madam. Thank you, madam. Thank you.
Okay. I think to understand a neural network, I think what is that neural network is? I think biological, all of us, we are born with a big structure. I mean, hardware with us. That is our brain. In the process of learning, what is that in the what do you, I mean, in the research or otherwise in the past happened is around 19. There is a fascination for for all of us to understand how it is working, how our brain is working. I think it's more than so long. That's a fascinating problem. Based on that, what the understood is there are several. I think all of us know that. Maybe some of us are. Maybe we know that each of the functions with respect to um, our brain are focused in certain areas. Like there is a cortex and the cerebellum. I mean, there are areas. What it means is that each portion will be taking care of certain aspects. Some will be like, I think, especially most of us have the experience of having a problem. Having a problem. Some disturbance, please.
Supriya madam, please switch off your mic.
Madam. I think some of you might have experienced, I think, if you have any side problems, especially you will have a neck pain. Mostly because the all the image processing, that means whatever the input we have taken will be happening at the back of our that is the portion where the image processing, or otherwise occipital brain we call it as, that is the portion, that is the space which happens this image processing. So that's the corresponding nerves which will be strained, because what is that the beauty of our design is that all our organs will sustain. They don't tell anything to us, but they will be working at best. So that's where, because you have the weakness, still the nerves and processing are been happening. That's the load it is been happening. That's where the pain comes to the neck. So that means what I mean to say is every portion of it has been taking care of certain work. Maybe our voice, or otherwise our language processing has been done at some places in our brain, and then our motor neurons, our reflexes, all these things have been taken care well by I think wonderfully. We feel, I think we always see the creation which will be happening without our knowledge. I think even the child, I think that's the basic understanding which fascinates. And then that's where the biological neuron understanding they have started. And then whatever the working model they have, engineering, always we do approximations. They will try to approximate this sort of a model into an artificial neural model. So that is what is the artificial neural network. That's where from there onwards it is mapped down to further deep learning right now, whatever state we are seeing in right now. So I have put it everything roughly. That's where the simplest basic unit, we call it as a neuron. How it works, maybe in the biological space, it works in a there are several issues associated with that one, but you can engineeringly model or approximate that as a, there are certain inputs it is taking. There is a neuron which is it is taking. There are inputs it is taking, and then it is summing them, and then based on a threshold value which is being incorporated as bias, and then it will be giving an output which is equal to 1 or 0. That is means on or off. We call it as. That's how it has been. A simple neuron is modeled. So then this, because our brain has not one neuron but 10 power trillion connections are there, 10 power 11 billion neurons, and then the corresponding connections are much more. So these are all connected. So neural network architectures are that these neurons are being connected in a certain manner, so that the output is what is the task you are giving, because you are giving, you don't know the architecture, how our in our brain, and how the connections are there, but there is an input. I am seeing this image and I can able to recollect that it is a bottle or something, phone, I'm telling. So but it is doing, but I don't know the architecture, but it is giving us output. So this sort of a connection, how best we can do artificially, that's where is the I think deep learning is going. I think simplest example I can put it is to understand you for this area is like a child born. I think he will be continuously seeing if as he grows. In the beginning days, he could be able to. If he need to know that he, I mean, understand that this is a ball, then you've been giving that information to him or her several times. At certain time, when the brain learns or network connections establishes, then he could be able to identify the next time as that it is a ball when you ask him. That is what we are trying to do in a artificial manner. So we are giving a huge databases like ImageNet and huge image, and then there is an architecture available and then available to it, and then we want to make sure that the architecture should say it when you show certain ball as a ball. So for that one, we are it doesn't happen for all of us as in one single go. That is what is the learning or training in terms of artificial neural networks. You will be giving again and again, so that until unless it recognizes correctly, that learning will continue. Okay, that's the simplest way I have made it. So this is the concept we will be using in the deep learning. Now for this problem of finding the DOA, so that you can beamform and beamform the weights, you find it out. I can apply this sort of an architecture to the problem. So I'll come to the problem now. How this problem at hand can be mapped onto this problem. Okay. I told you that we are taking a 4x4 antenna. So that means there are 16 elements, and then corresponding I'll explain. So for this model, I think there is some notation which you need to understand, so that the other equations will be easily followed. There is a desired signal, as denotes that there are direction of arrival of the signal theta, and finally we call it as azimuth and elevation, and W, it is like beamform or weights, so that you what are the weight combinations, that is what you need to find it out. And and X denotes the observed at any array element, and Y denotes the beamformer output. So S is being transmitted, X is the one which is received from each element. Okay, so in beamforming or otherwise direction of arrival estimation, we can understand this Because what is the purpose? I mean, I told you that we have 2 years. Based on that, we are trying to find the direction. In the thing, when I'm mentioning that one, how it finds, because if I'm changing my position, the direction by which I rotate my head when somebody calls me will be differing. So the information lies in the location of these elements. That's the point, already known point, that you need to take it. So that means the information about the direction is lying in the location of me, or otherwise location of my 2 years. Because if I'm changing my position to be the same, my user might be I mean, the calling person will be standing at the same place. But when when I'm moving my position, obviously the direction to which I need to rotate my head will be changing. So that means the information is embedded in the location of the antenna elements. What I mean to say. So for that one, that is what you need to, that is what we call it as a array response vector. I think that is for a rectangular array, we call it as the A theta phi, because it depends on the location. M and N stands for the location of the antenna elements. So all these things are, so that means there are 16 elements, means you will be getting the 16 array response vector, where the information is embedded in that one, where you use this information and combine them such that you will find the direction, or otherwise find the angle. That's the crux of the problem. Okay, so array response vector is a bar theta comma phi. There are because we are using 4 by 4, 1 1 1 2 1 3 and then 4 4. So how we calculate this array response vector is e power j m minus 1. These are all the values. K dx is the distance in the x direction, and then k dy is the distance in the y direction, because we are placing the antennas in an array. And then theta and phi, because you can directly calculate which direction it is coming. If you know, you can calculate these values. Okay, so what is happening is, the problem is that whatever is the signal is s of k is being weighted by these values, and then that is what is the antenna is receiving, because based on this is the embedded information A, which has the position information. Based on the position which is known, because the antenna array elements, you are keeping them with what spacing, what location, everything is defined with respect to reference. So this is known. This is what is that you receive is that signal is multiplied by this array response vector is what you receive. Now, because you are receiving the signal, because if you see that you are receiving this x of k from different antenna elements, y of k is the sum of all these things. Here it is not written as sum, but these are the vectors, vector multiplication. So it will be becoming the row matrix and column matrix multiplied with, it's like a dot product, and then it is a dot product, and then you will be combining them, and then you will be getting the received signal. Okay, if we understood this expressions, which tells us the location defines the array response vector. Array response vector signal, whatever is being transmitted, is multiplied by array response vector, and then that is the signal which the antenna is receiving. And the antenna, when you are beamformer output, is the combination of all these things. When you are receiving this signal, you need to find out the theta and phi. That's the problem. Okay, for this one, what is that we have done for using the ANN, because in several other methods, which are traditional methods, we can use like we will be finding out the mean square approach, LMS algorithm, adaptive way, LMS algorithm, everything we can do. But we are here when you are using the ANN for this one, how it is being done is like there is because we for all these things we need to, for all these things like in images, if the child need to recognize, you need to show the images. That means data. It is the data you need to create. So first of all, how we created for this data is, there is a 4x4 antenna elements. So then what are the directions? Theta and phi, what are the directions we have taken so that we get that array response vector is like we have used the previous expressions, like azimuth we have taken in the from 15 to 345 in the intervals of 30 degrees. Because you can do for 1 degree also, but this example shows this results. So 30 degrees, and then elevation, it is being shown with, it starts from 15 and then up to 75 degrees with an interval of 30 degrees. I hope this shows the grid of values, and then the entire, if you see this one, the entire grid values are 36 points, because from 15 to 345 and there are 12 points to go to this one. So that means 15, 330 divided by 30, 11 means including 1 point, so 12, and then there are 3 elevations, 12 into 3, 36 points. Okay, so all these theta and phi directions are being taken, and then we see this one, elevation 15, azimuth is being changed 15, 45 and so on. Elevation 45, azimuth is being changed from 15 to 345, elevation 75, azimuth. These are the combination of theta and phi angles we have taken further in the array response vector. And then, because these are the what is that purpose of our architecture is that this 36 directions, it should be able to recognize 36 directions, it should be recognized based on what? Based on the input received from the antenna elements. Antenna elements are, there are 4x4 means 16 antenna elements are there. If you put that antenna array response is a complex quantity, you can write it as the real and imaginary, so it becomes the 32 values. So based on the combination of these 32 values of the array response values, and what is that, it maps to which angle, which theta and phi. That is the mapping optimization problem we have done with a simple one hidden layer architecture, which is we verified with the different sizes of the architectures. I'll show the results. So I hope I'm once again reiterating this one. Our input is array response vector defines, because I told you that based on the location, based on the direction, the information is embedded in the array response vector. So array response, what values it will be taking for corresponding theta and phi, you can calculate. Those are the, because why it is 32 is because there are 4x4, 16 elements. Each is a complex quantity. So 16 into 2, real and imaginary values are, we have taken 32 values. And this, once you have this 32 values combination, which direction it is talking out of whatever our data we have created. Because we have created the array response vector for all these combinations, and then make sure that this leads to certain direction in this, out of this 36 points, 36 combination of theta comma phi, azimuth elevation. That's the problem at hand. So the simplest problem when we are to start with, what is the correct value? For that one to start with, you need to have the initial weights of all these architecture, because each one of them input neuron is connected to the next layer neurons by weights. So what combination of weights will be giving us this output is what you need to find it out. In signal processing point of view, you can find it out because there is a desired signal, and this is the received signal, and then what is the error between them, we will be using, trying to find out a minimizing them, that we called is the mean square error, reduce minimum mean square error criteria, which gives us the Wiener filter combination is the simplest one, R inverse into R into XT. We call it as the R is the autocorrelation matrix, RXT is the cross correlation between the received and the desired signal. Okay, so we have initialized all the weights with this minimum mean square error criteria. Then we have given for the we have used the back propagation algorithm to find the weights, final weights, so that we iteratively train the architecture with the given data set, and then we have found it out these values with respect to ANN. This shows the exact DOA which we have obtained, which we have tested, because in all the neural networks we talk with respect to training data, testing data, and also training before testing. We also validate 10% with validation also. The combination is 60, 20, 20, or sometimes 70, 10, or 20 times the combination of the percentage of data for verification and testing. So this is the test data. We have used around 10 test points. Test data we have used like 40 and 15 azimuth and elevation angle. And then we have seen for a different number of hidden layer neuron size, because the input and output layers, I have mentioned that 32, 36, that how many output neurons, there is rough estimation of how many neurons we need to take, but we can verify with varying the number of hidden neurons. So this has been done with n equal to 80, 90, and 100. And then we have seen azimuth and elevation. What is that it is giving for each of these test patterns. You can see that one. These are the results for rectangular array. We have also done for a circular array DOA estimation with 40, 15, all these 10 cases we have done for even the circular array with 8 elements. So we have formulated also the mean square error associated with each of this combination, rectangular combination and circular, around 0.016. Even adaptive antennas, we will be minimizing this error that we have done. That's the same problem. We are doing it for using neural networks. And then this network is also being verified too. This is like DOA estimation we have done in the front end, then used these weights to find. We also use these architectures to find out the weights so that we can beamform in a particular direction with having a null in a particular direction of interference. Both the things we have done. Desired direction is 50. We have the 50 degrees, and interference direction is in this is minus 50 and 50. And then the corresponding weights are obtained from the neural networks, and then weights obtained using ANN. So corresponding weights if I'm using MMSE, and then corresponding weights if I'm using ANN, and then what is the magnitude of those weights are being shown. And then this result shows with respect to, we have done all these simulations with respect to MATLAB. This shows the desired direction in minus 50 by using the weights to be able to give the desired beamforming in this direction, and with a null in a 50 direction. And also desired direction 30 degrees and minus 20 is for the interference. So this is what we have verified for the different results, different desired directions and interference directions, and we have tabulated these results. So I think further, I mean, I hope maybe I'm able to give you some of the information which are related to some of the research problems and research focus on research problems. Also, some glimpses of what we can do with neural networks. I hope I'm giving some clarity on these things. I'm now open for any questions, I think.
Participants, do you have any query or question? Participants?
Yes, sir.
Hmm.
Good evening, ma'am.
Good evening. Good evening.
Yes, ma'am. I'm having one doubt that
Yeah.
in case of hybrid beamforming,
Mhm.
if we apply different types of array pattern, like a rectangular array or circular array, so which antenna array pattern is better?
Which antenna pattern is better?
Out of
Hmm. Out of
yes, ma'am. This linear array and circular array. Linear array, then
Rectangular.
our rectangular array and circular array.
first of all, I think you need to understand one more thing. Like there is a what we call it as a if you I think all of us we have some then this name I'm not getting that correct word, but the thing is what is that I'm going to tell is like sometimes it happens like when you are being called when your direction is symmetric, I mean your pattern is symmetric in such a manner, then what happens is that the signal may be coming from the front, you may feel it as a back. You might have experienced this sort of things in when you are there. So this sort of a symmetricity will be there in terms of a rectangular array, but that symmetry ambiguity is not there when you are going for this circular array. And then other things to choose think are the frequency of operation. First, what frequency of operation you are going to use for your simulations are in real time, and also the spacing between the antenna elements. How much is, because when it comes to the circular array, it is the radius which defines the separation between them, radial distance between antenna elements. So because radius you need to know, and the separation between how you need to place on the uh, diameter these antenna elements. So that spacing matters. And when it comes to the rectangular area, what is the inter antenna distances in all these direction, x and y directions. So what is feasible, we need to verify for our particular problem with respect to what frequencies we are operating. I hope it gives some information. Before
Madam,
Ma'am, if the frequency is same, suppose I am using 28 gigahertz frequency and the antenna array spacing is same.
antenna array
Actually,
spacing, array spacing is same, but the thing is the pattern, not antenna. That's what I'm telling you. X and Y direction. When I'm saying the distance is not same as the radius of the circuit and the spacing between the antenna elements. It all depends on the if you, when you are working on circular, you want to put it in that perimeter, how many antenna elements. Both the things, it cannot be the same spacing. Even the
yes, getting actually, yes, ma'am. The circular array we are considering the radius, na properly, and in case of rectangular array we are not considering that.
so the,
Yes, right.
the
Ma'am,
spacing is not same. Okay.
yes. Ma'am, one more question that in case of rectangular array, the paper which I am referring, in every paper the antenna array pattern is like 4 by 4 antenna, 8 by 8. Instead of 4 by 4 or 8 by 8, can I consider it as 15 by 15, 7 by 7 like this?
Instead of Okay, even number you want to consider.
Yes,
We can
because yes, yes, ma'am.
I think in the simulations you have the full freedom to verify with all the values. But theoretically speaking, always why we prefer this even number and power of 2 is our signal processing algorithm, DFT and FFT, because there are built-in chips which are with the DFT sizes which are powers of 2. So that's where if you want to really incorporate into a hardware, we always goes with the powers of 2 because there are available hardware. You will be because every time why you go for hardware is the computational speed. No? So that's where it is preferred. But in simulation environment, you are free to explore and free to run in any manner.
Okay, thank you, ma'am. Ma'am, if possible, please share your email address in chat box.
Yeah, surely.
Yes, thank you so much, ma'am. Thank you.
Any more queries?
Participants?
Madam,
Oh.
my doubt is
Yes,
when
yes,
we are estimating the angle of arrival,
Mm.
since it is a wireless scenario, we will be having multiple paths.
Mm.
Significant angle of arrivals might be not a single pair. It can be means if we include azimuth and elevation, we will be having n number of pairs which are significant. But in this algorithm, we are only considering one pair, only one azimuth and one elevation we are considering.
Mm.
But in general, if you have L multiple paths, then we can have n azimuth angles and n elevation angles which are significant.
That is true, madam. But what we need to think of is that what is the correlation? Surely that whether they are coming, those multiple paths are coming in the same time or not, coherence time or not. All those things will come into picture. It is in terms of what frequency we are operating. Because in
Within
this
the coherent time also, we may get multiple paths.
within the coherence time if you are getting, then obviously what you need to take care that you need to multiple paths. I mean, one is surely if it is taking a more path length, then it can't come in the same time. Multipath means one is direct path, another is reflected from some other thing. So obviously its path length is large, then it can't come in the same time. Or otherwise, it is we can also think of like coherence time. So coherence time is one more thing, and then I think even the direction is also not same because obviously when the one which is having taken the reflected and coming, it has some other direction.
Yes, madam. Single is non-line of sight paths may not be single path. It can be multiple paths, and they may get constructively or destructively added here at the receiver.
But 5G, what is that? Is that for this millimeter wave communications, almost like we are in a small microcell places. So all the multipaths will come in the coherence time, and the signal processing algorithm can take care of it.
Can we implement the same algorithm by including this intelligent reflecting surfaces?
Yeah, intelligent reflecting surfaces. I think the purpose of these surfaces is twofold. Not alone you beam the signal in a particular direction and avoid interferers, also eavesdroppers, because nowadays I think the security is also a matter of interest for us, because there are so many users which are being which are
As it also requires the angle of arrival to be estimated so that the reflecting surfaces can radiate it to the user at that angle.
yes, you need to. That's why both the things will be done at the even at the base station, even at the mobile user unit. You need to have a direction of arrival estimation. Then only you can beamform your information. So both the things will be done. So you will understand what is the direction it is doing, and then we will be using that information to so that other it's not in eavesdropper also. That is another I think intelligent reflecting surface is somewhat I think in our millimeter wave communication we are in a because it is being I mean binded and blinded by this all different objects. Then still you want to use get the information I mean, to the user continuously. That's where the another hardware is being added so that you have a seamless connectivity. Where the intelligent reflecting surface need to do from which base station it is receiving, and then it should have the information of the user's information, and parallelly it should also direct the beams within that room environment.
Yes, madam. For blockage reduction, we will be using this.
Yes.
Thank you, madam.
Participants, any further questions? Participants?
Okay. Okay. Then.
Okay. Then, ma'am, I would like to say thank you. Thank you, respected Dr. A. Rajni, ma'am. Your presentation on implementation and evaluation of phase antenna array for 5G application was not only informative but also very engaging. We have gained valuable insights that will surely contribute to our professional growth and understanding of the subject. On the behalf of ECE Department, Samskruti College of Engineering and Technology, I would like to extend our heartfelt thanks to our speaker, Dr. A. Rajni ma'am, for sharing her knowledge and experience with us. Thank you. Thank you very much, ma'am.
Thank you very much, Anup. And also thank you very much, Vanisri Madam, HOD of Samskruti College. And
Thank
also
you, madam. Thank you so much, madam. You extended half hour extra, madam.
Okay,
Okay, no problem, madam. Madam is
hope
waiting.
it is, hope the audience could be able to actively participate. Thank you very much.
Thank you, ma'am.
Okay, thank you, sir. Thank you, madam.
I'm ending the meeting right now.
Okay.
Okay, thank you, madam.
Okay, for participants, just within a few moments, we will be starting our third session of today with Dr. A. Anuradha ma'am, just after a few moments.
Stop the recording. I will call madam. Okay.